Hi, I'm Mr. Orr, and today we are looking at section 11.2 in your geometry book, which is areas of regular polygons. To start with, the first theorem in this section is area of an equilateral triangle, and there is a formula for that, which only uses the sides. Now remember, normally a triangle is 1/2 base times height, but in fact we don't have a height here. What we're going to do is to create a height and figure out how we might use the information given, which is just the side lengths, in order to find the area. Let me see if I can make a slightly better, that's a little bit better, okay. Now, right angles here. Now because it's an equilateral triangle, if this side is S, then each half of it must be 1/2 S, okay? This is also a 60 degree, it's a 60, 60, 60 triangle, because of course any equilateral triangle has all three angles of 60. That means if that's 60 and that's 90, this must be 30. Now, you should recognize a 30, 60, 90 right triangle here. And remember that opposite the 30 is some number x, the hypotenuse is 2x, and the side opposite the 60 is x square root of 3. All right. In this case, we know that this, and I'm looking only at this triangle over here on this side, not the entire triangle. I'm looking at this right triangle here. Opposite the 30 degree angle is 1/2 S. Twice that is S, so that works. And this one is then S, 1/2 S, square root of 3. Let me write that a little bit better here. 1/2 S square root of 3, because x is 1/2 S, and this is x square root of 3. So it's 1/2 S square root of 3. Now notice that we can find the area, because we have an altitude, and it's labeled in terms of S, and we have the base. So if we take area, let's get rid of some of that, area of this equilateral triangle is 1/2 the base times the height. This is the base, this is the height. I mean, this is 1/2 the base, this is the height. 1/2 times 1/2 is 1/4. We get 1/4 S squared square root of 3. There. Now you have a formula for finding the area of an equilateral triangle given only a side length. That's all you need right here. Okay, 1/4 S squared square root of 3, that's the area of an equilateral triangle. Now, we're going to extend that to a multi-sided or polygon. So I'm going to make here a 6-sided figure, 6-sided polygon, okay, and I could do a little bit better than that maybe. Okay, we're going to pretend that that's regular, even though I know my drawings don't look very regular. But let's bring that over here a little bit. Let's bring that over here a little bit. All right, so pretend that's a regular hexagon. It has in it an internal line or line segment, which goes from the center out to, wait, now I can do a little, this is regular, remember. So it goes from the center out to a side perpendicular. This is called the APOTHEM apothem. All right? Now it also has this figure, this line segment here, which is a radius. And the reason it's called a radius is because if I drew a circle around here, that would be a radius of the circle. Okay, right here. From here, center, out to the circle, that would be a radius. So we have an apothem and we have a radius. Now, in order to find the area of this figure, no matter how many sides, as long as it's regular, we can say the area is 1/2 the apothem times the perimeter. So I'm going to label this A, this is R, this is S for side length. All the sides added up together give you the perimeter. So the area of the figure is 1/2 the apothem times the perimeter. Now that really has to do with the fact that there are a number of individual triangles in here, if I did this, and each one is 1/2 the base times the height, which is, now we're calling the apothem. So if you add them all up, this is what you get. Let's take a look at the use of that formula. If you are given the apothem and the side length, it's very easy. Let's find one where we have that information, and we'll start with an easy problem here. Let's say you are given that, let me find a figure here. Let's see, find the perimeter. All right, let's just make one up here. Let's say that the apothem here is 6, and that a side length is 10. Now, all we have to do in this case, we're given enough information, 1/2 area equals 1/2 apothem times perimeter, so that would be 1/2 times the apothem, which is 6, times the perimeter, which is, we have an 8-sided figure, 1, 2, let's see, 1, 2, 3, 4, 5, no, I'm sorry, 6-sided figure. So we have 60 is the perimeter, just one side length times 6. So that's 3 times 60, that would be 180. And so the area of this figure is 180 units squared, whatever those units are. Now, the trick with these comes in if you don't have all the information given, and sometimes you have to figure it out. So let's take a different sort of figure here. A 1, 2, 3, 4, 5, let's make an octagon. 1, 2, 3, 4, 5, 6, 7, 8. And we're going to pretend that's regular. And I'm going to give you a radius of 11. Radius of 11. Now, I need, remember, the apothem. I'm going to draw this to show you. We'll need that in a moment, perhaps. All right, now, I need the perimeter. So I need the apothem, and I need a side length in order to find the perimeter. You are given that the radius over here is 11. Here's what we're going to do. Now watch carefully, because we're going to use SOHCAHTOA in this case. I have a number of central angles here. Let me draw them all so you can see them. All right. Now, I have 1, 2, 3, 4, 5, 6, 7, 8. That makes sense because I have 8 sides, so I have 8 central angles. Each one of those is going to be 360 divided by 8. And I believe we did that a little while ago, and that was 4 times 8 is 32, 45. Each one of these central angles is 45 degrees. Okay, 45, 45, 45, and 45. And then this whole angle here is 45. But notice what we're interested in is the right triangle over here, because I have a right angle, and SOHCAHTOA uses right triangles. So half of 45 is 22.5. So each of these two is 22.5. This angle and this angle, because the whole angle was 45. Now, what I have here is, if I want to use SOHCAHTOA, remember I need this and I need this, both of them. So let's start by saying the sine, let me go over here. The sine of 22.5 is equal to, opposite, we'll call that x for now, over 11. X over 11. Sine is opposite over hypotenuse. Now, I'm going to run off screen for a moment here and get a calculator, and I'll be right back. And now I have my calculator. So I'm going to do, first I'm going to make sure I'm in the right mode, which is degrees, and I am. And then I'm going to do sine of 22.5 equals, and then I'm going to multiply that times 11, and I get 4.21. So what we found here, 4.21, is this length from here to here. I need to double that to 8.42 to get a side length. And then, since we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8 sides, I multiply that by 8, 2 times 8, 16, 4 times 8 is 32, 33, 64, 65.36. So the perimeter up here is 65.36. Now, I need to find this, the apothem. Now I can do that with trig, or I can do it with the Pythagorean theorem. I'm going to go ahead and use trig here. So I'm going to say the sine of the cosine of 22 and a half is a over 11. Cosine of 22 and a half is a over 11. That is adjacent over hypotenuse. So I find cosine of 22 and a half, cosine of 22 and a half, multiplied by 11, 10.16. So apothem is 10.16. Now, in order to solve this problem, all I have to do is plug those in. I have area equals 1/2 times 10.16 times 65.36. So if I multiply that out, I get 0.5 times 10.16 times 65.36 equals 332.03. That would be the area of this figure. And let's just see. All right, 332.03. Might be a bit of rounding there. I see it doesn't exactly agree with the book, but it's pretty close. All right, that should do it for this section. And the next time we will be looking at we'll be looking at arc length and sector area. So I'll be back. Thank you.